Okay, so today I'll be deriving the rocket equation. For starters, the rocket equation is simply delta V equals V E ln m1 m naught over mf. So VE is simply the exhaust escape velocity, the velocity of the fuel as it's being burned that's leaving as it's leaving the rocket. M naught is just the initial mass of the rocket, and MF is the final mass of the rocket as the fuel is being burnt. So we can just draw a diagram of our rocket. So this is a box. It has m mass and it's going at a certain v, and we could say it has an initial momentum before the mass is being burnt. Then let's draw another diagram. This case with the fuel being burnt, and now it's m minus dm, which is the ejected fuel, which is always changing. The amount's always changing, and then we can draw dm, and they have different velocities now, which is the new velocity of the rocket's v plus dv, the changing velocity, and the velocity of the fuel is v minus u, which is simply the velocity relative to the velocity of the rocket. And we can call this the final momentum. And knowing that momentum is conserved, we can say pi equals pf. And from here we can make an equation. We can say mv equals m minus dm v times v plus dv, and then plus dm times v minus u. And then we would just go about expanding this. And then once it's expanded, it looks like mv equals mv plus mdv minus vdm minus dvdm plus vdm minus udm, and then we would just simplify further, which is mdv minus dmu equals dmdv. And we know there's two differentials being multiplied, which are both approaching 0, so it'll be a very small number, and we can assume it to be 0. And then we would rewrite the equation as mdv minus dmu equals 0. And then we can rearrange for dv. So we get dv equals u dm over m. So how do we get delta v from this? We'd have to integrate. So we'd integrate the first side, dv, with the upper limit v2 and v1, lower limit v1, and it equals to the integral of udm over m with the upper limit m2 and m1. So after integrating the left and the right side, you get delta v equals, you can bring the u outside the integral, so u times the integral of 1 over m in respects to m. And we can say that it ends up equaling delta v equals u times ln m, and we still haven't dealt with the upper and lower limits quite yet. So the next step would be saying delta v equals u multiplied by ln m2 minus ln m1. And then from here on, we can further simplify, and we can actually take a negative sign. We can factor out a negative from the function inside the bracket, put it outside the u, and then we'll get ln m1 and minus ln m2. And you'll see why we did that soon. From here on out, you can simplify it more. Using the logarithm rules, you can say delta v equals negative u times ln m1 over m2. And now we can replace the variables with our known variables from the equation, and we can replace u with negative VE. And we say negative VE because it's going in the opposite direction of the actual rocket. It's going in the negative direction. So it cancels out the negative sign outside the u, and therefore it's just VE. And then we can replace m1 with m naught and m2 with mf. Another equation that comes into play is sometimes the one involving the specific impulse, which is just how effectively a rocket uses its propellant, and we get that value in some areas, and that's simply VE over G naught, which is the standard gravitational constant. And then VE, we can rearrange it, and we can solve for VE equals ISP times GO, and then we would plug it into the original equation, which is simply delta V equals ISP times g naught times ln m naught over mf. And that is simply just another equation to look at.